Molecules and compounds are made up of different elements, and these elements can be present in different proportions. Now, what percent composition tells us is the percentage by mass of each element that is present in a given compound. So before we go into further detail about percent composition, we need to first talk about the difference between empirical and molecular formulas. So let's start with an empirical formula. An empirical formula is the simplest formula for a compound, and what this shows is just the ratio of elements in a compound. In contrast, the molecular formula shows the actual number, and this is something you're probably more familiar with, right? And the molecular formula is related to the empirical formula in that it's a multiple. So often you can multiply the empirical formula by a certain factor, such as 1, 2, 3, or 4, to get the molecular formula. So let's look at some quick examples. So the first is, so it says here, determine the empirical formula for the following compounds, and they give us these three guys, right? So the first case is actually glucose, C6H12O6. We can simplify this, right? There's a common factor of 6. Divide all these numbers by 6, we get C, 1. I don't need to write the 1. H2O, right? And we can do the same thing for N2O4. We can divide all these numbers by 2, so we just get NO2. And then lastly, for C5H12, there actually is not a common factor for 5 and 12, so I can't divide them by anything besides 1. So the empirical formula is actually the same, right? And so the reason I did this last example is just to remind you that the molecular formula can be the same thing as the empirical formula if there isn't a common factor. Okay, so let's do an example. And the first type of example we're going to do is going from the molecular formula to percent composition. It turns out this is a bit easier, and for the purposes of your class, it's going to be less common, so it won't show up on the test as much as the reverse. But it's still important to start with this because I think it provides you with a good framework. So the steps are, first, calculate total molar mass, which we know how to do already, then determine the mass of each element that contributes to the molar mass, and then divide to figure out percentages. So let's take a look at this example. Fairly straightforward. Calculate the percentage composition of C2H4. Okay, so let's go ahead and start by figuring out the mass that carbon contributes to the total and the mass that hydrogen contributes to the total. So we know that we have 2 carbons, so I'm going to write 2 carbons, and we know that the molar mass of each carbon is 12.011 grams, right? And so times 12.011 grams of carbon per 1 mole of carbon, that gets us to 24.022 grams per mole, right? We'll do the same thing for hydrogen, right? So for hydrogen, we have 4 of those guys, and we multiply by the molar mass, which is 1.008 grams of hydrogen per 1 mole. Here we have 4. And so we should get 4.032 grams per mole, right? This is of hydrogen, and this top guy is of carbon. And then if we add these two numbers, we should get our total molar mass, which will be, in this case, 28.054 grams per mole. And that's of C2H4. So here, in order to figure out the molar mass, which we just did, we added these two guys. To figure out the percent composition, we just take the grams per mole of carbon, divide that by the total. And to figure out the percentage composition of hydrogen, we take 4.032 divided by the total. So let's do carbon first. So for carbon, we're going to take 24.022 divided by 28.054 times 100, and we get 85.6% carbon. Right? And here, because we only have 2 elements, we can actually figure out what the other one's going to be. It's going to be 14.4%, because the percentages need to add up to 100. But we can also calculate it, right? We can take, for hydrogen, the mass that hydrogen contributes to the total is 4.032 grams. And we divide that by the total, which is 28.054, multiplied by 100, and we get 14.4%. So now let's do the same thing, but backwards. This time we'll be given the percent composition and be asked for the molecular formula. Okay, so the steps are a little bit different, and these are a little bit there's basically an extra step, but this is very important. So this type of problem is very common and very important, and it will show up. And it's a bit harder too, but nothing that you won't be able to do. Okay, so the first thing, you assume you have 100 grams. This converts percentages to grams because you're given percentages to start with. And then you're going to convert from grams to moles divided by the smallest to figure out molar ratios. Okay, and then once you have the empirical formula, you can convert to molecular formula given the molar mass. So let's just apply those steps to this practice problem. So it says, determine the molecular formula of a compound with a molar mass of 60.05 grams per mole. So this is the molar mass, that's going to be important. And then they give us the percent compositions, right? 40% carbons, about 7% hydrogen, and about 53% oxygen. Okay, so let's follow the steps. I want to assume I have 100 grams to convert the percentages to moles. So that's exactly what I'm going to do. So I'm going to start with my carbon. So I have, let's just assume I have 40 grams of carbon, right? If I have 100 grams total. And then I'm going to convert that to moles. So for every 1 mole of carbon, I have 12.011 grams of carbon, right? I'm just using that from the periodic table. And that's going to be equal to a certain value. Okay, we can do all these calculations at the end. We'll do the same thing for the hydrogen. So we start with 6.7 grams of hydrogen. And for every 1 mole of hydrogen, that's equal to 1.008 grams, right? Then we're going to plug that into our calculator. And the last thing we're going to do is do the same thing for oxygen. So we know we have 53.3 grams of oxygen, right? We use the molar mass. For every 1 mole of oxygen, I have 15.999 grams. That's a 5 here. And then after I calculate all these values, I get 3.33 moles of carbon. I get around 6.5 moles. So this is carbon, this is hydrogen, and then here I get about 3.33 moles of oxygen. Now these numbers right now, they might seem very unhelpful. Like, what are you going to do with these? The next step is to figure out which is the smallest. Here we have 2 values that are the smallest, and divide every number by the smallest number of moles. So here the smallest number is 3.33, so we're going to divide everything by 3.33. So here I'm going to divide by 3.33. So 3.33 divided by 3.33 is just 1. Here I'm going to divide 6.65 by 3.33. I get about 2. And then here I'm going to take 3.33 divided by itself, which is about 1. That yields us the empirical formula, which is CH2O, because for every 1 carbon and 1 oxygen, I have 2 hydrogens. Now we're not quite done yet, because this represents the empirical formula. So this is empirical, right? This is not the molecular formula. The molecular formula is the actual number of elements, okay? So the actual number of elements is something you can figure out based on the molar mass, okay? So what's the molar mass of CH2O, right? It's going to be 12.011 grams plus, which is from carbon, plus 2 times 1.008 grams, and that's from the hydrogen, and then plus 15.999 grams. And then when we solve for that, we should get about half. So we actually get about 30.025 approximately. And then when we solve, we should get, so we know that basically the molar mass is 60.05, but the empirical weight is only 30.025. And so we have to multiply all these numbers by 2, so we get C2H4O2. And that's our final answer.